Specifically, we're going to talk about A and B, talking about A and B. To reason about things, we can define the idea of a predecessor, so we'll say Pj, which is just going to be the argmax. Do you guys understand what argmax is? Yes, eh? Yeah, I figured so. The argmax, actually, I can see that in my notes. It's going to be the argmax of the, oh no, yeah, that's correct. Okay, argmax of the, we're just going to pick the max B such that, so let's just do it this way, such that the overlap of the jth element, so J and B is false. What we mean by that is so these are sorted by finish time. And if I grab a random element, what's the last element that doesn't overlap with this element? It's just this guy here. I should probably number them so you can participate if you want. How about 4? What's the last non-overlapping element? Yeah, I really drew it. Let's say number 1 just to be fun. Yeah, number 2 we'll just set P2 equals 0, and that'll be the convention. And I think that's all of them. I had a lot more squares here, but when you draw things with chalk and you get excited, then that happens. So this is something we can use. We can use this to pre-order. So use the, or to pre-populate. We can use this to pre-populate some data. So we'll say Pj for all j. So you just want to populate all of them in the set. And from now on, we'll consider, when we consider these activities, we'll consider the idea, I'll put it back down in a second. We can consider Aj such that start time, finish time, some sort of awesome weight that we want to maximize, and we'll have a Pj party. Does that sort of make sense? So all we want to do is we just want to have an idea of what's the last element that doesn't overlap. So when we're starting to formulate what these cases A and B, we can think broadly about what's the last element in the set we can consider, without running into our overlap. And that's the hardest problem of this whole algorithm. So everyone has this, right? No one's freaking out? Great. I think I'm much slower than you guys, which is perfect. My resolution this week was to draw more diagrams, so I hope you like them. Yeah, so let's form a recursive function. To maximize the profit. So the goal is maximize profit without overlap. So we're going to use this idea that we already have an optimal set that is smaller than our set to work with, and we're just going to form a really, really, really simple algorithm. It's actually kind of fun how simple it is, so you can see why people, when they're making donation screens, just write stuff like that down. And then why firms like mine get hired to come in to help out. Because it's really easy just to say if j equals 0, return 0. Otherwise, else. We're going to return the maximum of two values. We're going to return the maximum of this operation before us, or the current weight plus for our predecessor, which is the last non-overlapping element. So this takes care of the overlapping condition. I mean, I think that's it. It's really simple. Like compared with the greedy approach, it's a much simpler algorithm already. And it takes care of everything. It takes care of the overlap. Because our predecessors that we've pre-calculated, which I'm pretty sure we can do in linear time, you just run through the set and track the last one doesn't overlap with. Might not be true. Does that make sense to you guys? Is it totally weird? So the idea is that given any item, you know, in here, given item 4, we're gonna compare the recursive maximum profit that was yielded by 3 with the profit that could be yielded by 1 and by self. And whichever one's greater, so either, you know, this guy and everyone before him that doesn't overlap is greater, or this last one that doesn't overlap with me and everyone before that is greater. And there's no other possibility to consider. Like those are that's it. So if you just let that calculate, it will work. It seems pretty simple. Like there might only be, you know, 1,000 items in a set. So that's not a difficult calculation to run through. In principle. And the next thing I want to show you is why that is a terrible idea. Just really quickly. So if we take the idea that Rj equals rec off j. So if we consider that we're running the algorithm recursively here, and we're going to denote that as Rj, then you can see, and let's just say that Pj in general is just j minus 2, let's say. It's just 2 back. So the last 2 are in the way every time. So you can really quickly, I'm going to draw a few of these. So this will be R9. But it's useful to draw it out one time, just to get an idea in your head of just how terrible this is. So the other side we'll consider R8. This will be R7, and this will be R6. But then this will have more, right? So these guys will have more, and this is in the way. So these have more, and then these also have more. And right away we can see, we already at the top, we're seeing tons of duplicates. You know, oops, I don't know why I did 6 there. This one. And it turns out that even with 10, just with 10 items, you already get this massive tree, so it's exponential. So exponential time. So yeah, so that's why we don't do that. Luckily, and this is where we get into the idea of, this is where we talk about this, when we say overlapping subproblems, this is overlapping subproblems. And so when you're considering your proofs or your approach, this is overlapping subproblems. It's in the execution of your recursive solution. that's the point in which we're talking about overlapping sublevels. So if you had to consider, all the mixes and matches between these problems, and subtract one element here, add another element here, and then you end up with these situations. Because intuitively we know that there's only 10 of these. There's only 10 of these values to worry about. So why are we calculating 40 or 70 or whatever it's going to end up being there? Yeah. Does that make sense? Actually, never mind. Okay, cool. I'm looking at the time, so I know that we'll be allowed. So I hope I've motivated you and got your attention. So it turns out that this is where we can get the idea of memorizing values. Does anybody know what this is, memorization? Can anyone tell me what that is?
Basically store the results of data.
Yeah. Basically, so there's kind of, yeah, exactly, that's exactly it. Yeah, we're just going to use some pre-cooked data. The entry level to this sort of technique is the idea that you just want to make it so you can compute each value once. And the original idea is really, really, really simple. So the idea is that you first just want to initialize some values. So if we consider we have, some optimal set, we're just going to say for all the j's, we'll say it gets the value of those. So we're going to say that, oops, no, that's right, okay. That's 0. And then, so now when we do our recursive algorithm, we'll still use the recursive algorithm. So put it down here. I'll just use an n index for kicks. Oh my goodness. There we go. I'm just going to write MRO because I'm running out of space on the board, but I think you guys are pretty smart, extensively. And there's going to be some P that we've pre-populated, and I did it, sort of. So, what do you guys think about that function? Has no return value, that's one thing. So that's a key part of any algorithm, right? Yeah. Any thoughts? Thoughts, comments, concerns? So the benefit is definitely that it avoids this problem. Would you say it's the best algorithm for this problem? Leading question. I mean, when you program a recursive algorithm, there will always be, you're always going to push local variables like n. Like you're going to push this on the stack, right? So depending on your algorithm, if you form a solution like this, you're gonna run into a bottleneck eventually where just the idea that you're pushing local variables over and over and over and over and over, even though you buffer some of them, in an array of size n, let's say, you're gonna run into problems. The benefit of this problem is that, well, we'll talk about the benefits in a second. I'll show you the second algorithm in a minute. But first, I think this is probably the best time to take a break. So I want you to think about that for a second. Let's take a little 10-minute hiatus.